So welcome you back. So far we did invariant estimation for three kind of probability models. The first one was location probability model, then the scale probability model, and then location scale probability model. And we realized that principle of invariance is useful when the estimation problem at hand has a nice structure in terms of certain group of transformations. In that case, it is possible to restrict the class of estimators under consideration. And in certain situations, then you may be able to find the best estimator, or at least you'll be able to further restrict the class of estimators which one should consider. And we saw that in all the three examples, that is location probability model, or a scale probability model, or a location scale probability model, it was possible to get the best invariant procedure or best invariant estimator. So that was all for invariance which is pertinent to this course. I'll try to do a few more problems so that you can get further insight into how the invariance principle has to be applied at various situations. But before that, let me do a couple of problems related to the theory which we did for better understanding of various results which we derived. So let us take this example. So what you have is, you have a random sample, x1, x2, xn, which is IID, normal, mu sigma square, right? Where theta is mu sigma, which belongs to R cross 0 to infinity. So in a sense, this is your parametric space. Now we have to consider, last time we considered example where we considered estimation of mu with respect to a general location, affine invariant loss function, W of A minus mu by sigma. And I saw that for even such a general loss function, the best affine invariant estimator of mu would be x bar. Now let us take the invariant estimation of sigma square. So G is a affine group of transformations. Which is basically collection of all the transformations of the type GBC, where B is positive, C is in R, and GBC of x1, x2, xn is same as Bx1 plus C, Bxn plus C, where vector x So we have seen that under this affine group of transformations, normal probability model being a location scale probability model is invariant. Why? Because you can look at the density over here, f theta x turns out to be product I is equal to 1 to n, 1 by sigma root 2 pi e to power minus xi minus mu by 2 sigma square. This is what the density is, x belongs to Rn, which can be written as 1 by sigma to power n, f of x1 minus mu by sigma, xn minus mu by sigma, x belongs to Rn. So it is of the form of the location scale family which we considered. And what is your f of T1, T2, Tn over here? F of T1, T2, Tn is nothing but e to power 1 by 2 pi to power n by 2 e to power minus half summation I is equal to 1 to n Ti square. Right? So it is a location scale family. Now if that is the case, we know that the set of probability distributions is invariant under this group of transformations. the problem of estimating mu is invariant. In general, problem estimating sigma to power r is invariant. And since I'm talking about estimation of sigma square under the loss function L theta A, which is nothing but A by sigma square minus 1 gamma square. So here Wt is nothing but T minus 1 whole square. Because we have seen that this problem is invariant under the loss function W of A by sigma square, right? So for invariance, you need L theta A to be of this type. Under all this, you have an invariance. So this loss function is of this type with W of T as T minus 1 whole square. So estimation problem is invariant. So one can find the best affine equivalent estimator of sigma square. Now we have seen that things are very simple if I'm able to find an estimator of sigma square based on a complete sufficient statistic. Now it is x1, x2, xn IID normal mu sigma square. So in this case, x bar and s square is complete sufficient. What is your s square? S square you can take as summation I is equal to 1 to n xi minus x bar whole square. So what is this and W is ancillary, right? So this and W are independent. So best by the result which we did, minimum risk invariant estimator of sigma square is, so I can take my delta naught x because I have to first find one invariant estimator of sigma square, scale invariant estimator. So I take delta naught x as s square. Now for this to be invariant, what I have to see? Delta naught of bx1 plus c, bx2 plus c, bxn plus c should be same as b square of delta naught of x1, x2, xn. So you can see delta naught of bx1 plus c, bxn plus c. So what would happen in s square is xi minus x bar. X bar of all this is again bx bar plus c. So when you look at xi minus x bar, cc gets cancelled. B is common, B comes outside, becomes square, so it becomes bs square. B square s square, which is nothing but delta naught of x1, x2, xn. So what does that say? This says that delta naught is in di. So I have an invariant estimator of sigma square, which is a function of a complete sufficient statistic. So what is MRI? MRI is delta star x, which is delta naught x by u star, where u star minimizes. Delta star psi u, which is E of 0, 1 W of delta naught x by u, which is nothing but E0, 1. Delta naught x is nothing but s square by sigma square minus 1. Sigma square is 1 because E0, 1. So s square, delta naught x is s square divided by u. This is whole square. In fact, you have seen this. What is a minimizing u star? Minimizing u star is nothing but E0, 1 s square whole square divided by E01 S square, which is E01. Under E01, what is the distribution of S square? When mean is mu and variance is sigma square, it is chi square on n minus 1. So it is expected value of chi square on n minus 1 whole square divided by expected value of chi square on n minus 1. What is the expected value of a square of a chi square? It is same as variance of chi square, which is same as 2 times n minus 1 plus expected value of chi square whole square, which is n minus 1 whole square, divided by expected value of chi square on n minus 1, which is n minus 1. So how much that becomes? You can take n minus 1 common, so n minus 1 gets cancelled from the denominator, and you get 2 plus n minus 1, which is n plus 1. So in this case, your MRI is delta star x summation I is equal to 1 to n xi minus x bar whole square upon n plus 1. Now let us see some very easy consequences. If I have to find the UMVUE, what is the UMV in this case? You know from your last course, this is summation I is equal to 1 to n xi minus x bar whole square upon n minus 1. Now this is also invariant, because you can see that bxi plus c minus bx bar plus c b again, so it is again satisfies this property. So it is invariant. And this is the best invariant. In this case, best invariant exists. So best invariant is unique. So this suggests that this would have smaller mean squared error than this, or smaller risk than this, where risk is given by this quantity. So what you get is r theta delta star x would always be less than or equal to r theta delta u m v u e for every theta, where risk is basically expected value of, where risk of an estimator r theta delta is expected value of delta x by sigma square minus 1 whole square. Right. So simple application of the result which we did for scale invariant of sigma square. Now let's try to see another problem.